So, now, one thing I want you to understand as we look at the fundamental theorem of calculus is this part that we're looking at is only one part of the fundamental theorem of calculus. There are multiple parts. This is the only one we're going to be using. So we're not going to refer to part 1 or part 2 or whatever, or the first fundamental theorem of calculus or second or however you refer to it, okay? We're just going to be looking at this part here. And this is finding the area under a curve, which we said is what an integral does, within a specific interval, okay? Now we said we already talked about indefinite integrals, and that's when we had that plus c, okay? We had the plus c because we didn't know exactly where we were finding the area. But here we have, you'll notice we have the integral from a to b. That's how you would read this. The integral from a to b. The larger number goes on the bottom, the bigger number goes on the top. Okay? This is what's known as a definite integral. Okay? And this is what we're doing. We're evaluating definite integrals. Okay? Now, a little bit with the notation. I want to make sure we understand this. I also want to look at the concept here, visualize it before we even get to some actual examples. Okay? It says here that the integral from a to b of f of x dx equals the antiderivative evaluated at b minus the antiderivative evaluated at a.
So integral.
Okay?
Like I thought the antiderivative and the integral are the same thing.
The antiderivative and the indefinite integral are the same thing.
So then
Okay.
why do we have, is that elongated s the definite integral?
No, this elongated s just means integral. If you see numbers next to it like this and this,
Then it's definite.
then you know it's a definite integral, and you're going to need, and that's important because you need to know, should my answer be an expression or should it be a number? Okay, if you see the numbers, it's a definite integral, your answer should be just a number at the end. Okay? Now, I want you to understand what happens to this, and I want you to see how this actually connects to something we did back in statistics. Okay? Let's say I have this random function like this, okay? If I am finding the definite integral from a to b, let's say a is a value here, okay? And b is a value here, okay? What I'm actually finding is the area between the x-axis and the function, but between these two boundaries, okay? It's just what we were doing when we were breaking it into segments on Tuesday. We were breaking it into those strips of equal width, and we were adding up all the areas together. Remember, that's what we were doing, and that's how we defined what the integral was. But I want you to understand what this antiderivative actually is going to give us, and that's where I hope you'll see the connection to our statistics. Okay? When I am finding capital F of b, all right, that's going to be a number, and that is actually going to give me the area under the curve to the left of b. Okay? So capital F of b is going to give me all this area to the left forever. Okay? Capital F of A, on the other hand, is going to give me all the area to the left of A. So I'm starting here at A, and I'm finding all this area. So why do I subtract them?
The difference is the distance from A to B.
The difference of those, yeah. The difference of those is the part just from A to B. Okay? Notice this capital F of A essentially gets rid of all the area we don't want. All the stuff to the left of A. Now, does anyone remember when we did this before with statistics? The normal curve? What?
Was it frequency?
Well, the normal was a frequency distribution.
It was like,
What did we do with the normal
it
curve?
was like,
We found the area under a curve.
but it was like if you want to have it from a certain point,
The cumulative something.
like in between, like if you wanted to have under 68%, then you would use it, you know.
Okay, do you remember what that function was? Cumulative was part of
Cumulative frequency.
the normal cumulative frequency distribution, normal CDF, right? Okay? So, we have, if you look at your normal curve, when you did the normal CDF, that gave you the area from whatever value you put in below. And if you had the end spire, it would let you put a left boundary on it, and that was really, really nice. But what did you have to do if you didn't have the end spire?
You had to subtract it from the normal PDF.
Yeah, if you wanted it between, well, not PDF,
CDF.
you had to subtract this left-hand side
1.
from what you got on the right-hand side, right? So, if I wanted between A and B, I had to use the normal CDF for A, and that gave me all this stuff I didn't want. And I got the normal CDF for B, and I subtracted them, and that gave me just the area in the middle that I was looking for. And that would, in that context, that area represented a probability. Okay? Now, guess what your calculator was doing when you hit normal CDF?
Integral.
It was doing an integral, okay? It was doing the integral. So, it's important to understand what's going on here, and that might kind of shed some light on what was going on back with our statistics too, okay? So, we get rid of this mess, and let's actually look at an example of doing this. All right, and we'll also see some notation that goes along with this, so it's important to recognize. So it says here, use the fundamental theorem of calculus to find the area between the x-axis and y equals x squared from x equals 0 to x equals 1. So I've got this function y equals x squared, and I want the area between 0 and 1 in the x-axis. All right, so there we have it. First of all, a good habit to get into is to shade the area that you want. In fact, I've even seen IB questions where it says, here's an integral, shade the area that we're looking for. Okay? Here you see the area. How would I write this as an integral?
The integral symbol with 1 and 0, 1 at the top. And 2.
Good. Okay? The integral from 0 to 1 of x squared dx. Okay? The integral from 0 to 1 of x squared dx. Okay? Now, let's use the rule we just learned a little while ago. What's the integral of x squared d?
1/3 x to the third.
Very good. 1/3 x to the third. Okay? Now, You're not going to do this when you do normal definite integrals like this, but I'm going to put this plus c in here just so you'll see what happens to it. Okay? And you'll see why we don't need to worry about the plus c when we're doing definite integrals. All right? So, a little bit of notation here. When you are doing this, a common thing is we will write a vertical line here, and we'll put the 0 here and the 1 here. That is notation that indicates that we're going to evaluate this integral we just got at 1 and at 0, and we're going to subtract them. Okay? In other words, it's telling us that we're doing capital F of 1 minus capital F of 0. All right? This right here is our capital F of x. All right? So if I plug in 1, what do I get here?
1/3.
I get 1/3 plus c. Okay? Again, in the future you won't have the plus c's, but I'm showing you why you won't need them later. If I plug in a 0, what do I get? 0 plus c. Okay?
Why do you do the vertical lines with the?
That's just notation that's commonly used.
So you do the S at the beginning and a straight line at the end.
Yeah.
Okay.
This indicates integrating. This indicates we're using the fundamental theorem of calculus. We're going to evaluate it here and here and subtract.
Okay.
Okay?
And the capital F's are equal for integrals.
Yeah. Okay? So now, look at this. What's going to happen with my c's when I do this? They cancel out. That's why when you're doing definite integrals, you don't need to worry about the c's. This is just going to end up being 1/3. Okay? So when you're doing this, don't bother putting the plus c because they're just going to cancel out anyways. Okay?
So like you can kind of ignore the dx because it's just like notation.
It is notation. You don't ignore it because it is important, and it will become more important if you take an advanced level of calculus where
You mean like
You're-
Lego?
you're having to use substitution later on and stuff. Okay? That is an important element of the notation, so don't ignore it.
Will I be able to plug something into where the X should be?
Actually, yeah, you do end up plugging stuff
And
in
then
for the
like,
dx.
you have to try and get it to equal the dx still, and it never does, so you have to add something in the integral, and it gets confusing.
Okay, so how do you write that? Like you just write like big line 1, 0 equals 1/3.
Yeah, like you could show like the 1/3 minus. It's not always going to be minus 0.
No, but
Okay.
you're saying like what's your final answer? Just 1/3.
Your final answer is right here. Yeah, 1/3. Okay. All right. So then, let's take a look at this one here. Again, we're going to sketch it, but we want the integral from 1 to 9 of the square root of x. I'm going to rewrite that as x to the 1/2 with respect to x. Okay? Now again, I'm going to sketch this. You guys know what the square root function looks like. It looks like this. All right? But in this case, I'm going from 1 up to 9. Okay? Now, obviously we know it crosses at 1, 1, and then it crosses at 9, 3. Okay? Just so we can kind of see it there. Okay, so I'm trying to find this area right here.
Okay.
So let's use our integral rule for the x to a power.
Why do we know the process at 3? Because it's the.
Well, you just plugged in 9. Square root of 9 is 3.
2/3 x to 3.
Okay, add 1 and you get x to the 3 halves. You divide by 3 halves, which is the same as times 2/3. Good. Okay? Everyone see how we get that?
In a line.
All right? So yeah, now we have the vertical line, and we're going to evaluate this from 1 to 9. Okay? In other words, we're doing capital F of 9 minus capital F of 1. So, I have 2 times 9 to the 3 halves power over 3 minus 2 times 1 to the 3 halves power over 3. Okay? How do you do a 3 halves power?
Is that the square root cube?
Yeah, it's the square root cube. The 1/2 power is the square root, the 3 is cubed. So the square root of 9 is 3. 3 cubed is 27. Good. So 27, 2 times 27 divided by 3 is going to be 18. Okay? So 18 minus, this one's easier, 2/3. And I get a total area of 17 and 1/3. Okay? Not too bad, is it?
And you would say that's the total area on the curve, or you would say that's the area from x equals 1 to x equals
It's the area from x equals 1 to x equals 9. It's just this shaded part that we have right here.
9. Sorry, that was a stupid question. To 3, to the 3 half over 3. That's 3 over 2?
Yeah, this is 3 over 2.
So
Okay.
is 18 the total area of the actual curve? Just from
Yeah,
the line
and
to
with the, since it's a square root function, actually, 18 would be everything all the way here. The square root function actually has a beginning here because it starts right at the origin. So that area equals 18. And then you have this area below 1. That area is the 2/3. Okay? So that's 2/3. And then what we found was the 17 and 1/3. Okay? The total thing would have been 18. All right?
How do you do it? To the 2 halves now?
The 3 halves. You got to think of it as 1/2 times 3. So do it to the 1/2 power, square root it first,
And then.
and then cube it.
Okay.
You can cube it first, then square root it, but your numbers get big. So 9 cubed is like 729, and then you probably don't know the square root of 729 is 18. Or no, that's it's 54. I think. I don't know. Anyways, you're probably not going to do it in your head, so it's easier to square root first, then cube it. All right, now, there are a couple of properties here I want to point out. None of these are like earth-shattering or terribly difficult, but there are some properties. Your eyes just got like twice as big. All right, they're not that hard, trust me, okay?
Show us to us like that. That looks so scary.
Well, here, let's take it one at a time. Look at this. The integral over an interval of only one value. Think about it. I'm going from A to A. What area does a line segment take up?
0.
None. Okay? If I'm going from A to A, that's just a line segment. It has no area at all. Okay? So that area is 0. Now why you would ever want to do that, I have no idea, but
IBSL.
now you know. Yep.
Well, then, like, if as the distance between the two parts that you're doing approaches 0, as as the change between them if you do the limit approaching 0 and then the integral approaches 0. And how do you, like, I get that the area is going to be of pockets of value because there's stuff under it, but just the summation of lines that are all 0 equaling a positive value doesn't make sense.
Well, it doesn't, because it's not like you can fill up a region with lines, because each line has no width. There's an infinite number of lines, it would never fill it up.
Yeah.
That's the idea. So you're not thinking of it in terms of lines, you're thinking of it as
Rectangles.
spaces or rectangles. Yeah. Okay. Here's another one. What if you put the numbers in the wrong order? Okay? In other words, instead of going from A to B, you're going from B to A. Alright? It's going to make the entire thing the opposite. Okay? Here's where, if you had a negative area, it's almost kind of like it's telling us a direction, right? Kind of like a negative derivative told us a direction of decreasing. A negative area would tell us we're going to from right to left instead of left to right, okay? Or another alternative is that it's below the x-axis. So there's more than one way you can get negative areas. This is one of them, okay? This is a more useful one, okay? One that you'll use a lot, but you won't even think about it, okay? And that is if you have two adjacent intervals, okay? If I have this function here, all right, and I have A, B, and C, okay? If I take the area from A to B, this area here, and then I take the area from B to C, that area here.
It's the same thing as taking it from A to C.
Exactly, and that's what this is saying. From A to B plus going from B to C equals going from A to C. Okay? So again, not too difficult, but there will be times where it's helpful to break it up. Especially, let's say you had a piecewise function, you wanted the area under the piecewise function, let's say, up to this point it was one function, but then right at this point here, it changed to the other piece, and now it's like linear or something like that, okay? You could break this, and if you wanted the integral from A to C, you could kind of go backwards and break it up into two separate intervals to integrate over, okay? Thinking back to geometry, that's our area addition postulate. The area of a whole region is the sum of the areas of the parts that it can be cut up into, okay? That's an old geometry postulate, okay? The integral of a sum or difference, all right? Remember, integrals are just giant limits, right? And they're limits that have sums inside of them. And both limits and sums had the property where if you had things added together, you could split them into separate ones, right? So, you can do the same thing with our integrals. If you have the limit of a sum or a difference, you can split it into two separate integrals with each part in a different integral. So, for example, if I'm doing the integral of e to the 3x plus x to the 4th dx, I could split that into two separate integrals, the integral of e to the 3x dx plus the integral of x to the 4th dx.
Kind of like the law rules. Yeah.
Okay?
Ish.
Kind of.
So
It's actually very parallel to our derivative rules too. Remember, the derivative of a sum is the sum of the derivatives. Okay? And actually, here's another one that kind of, I'll skip that one for a second, because this is the one I was looking for. Just like this one, the constant multiple. Remember when we had the derivative, if you had 3 times something, you could just take the derivative of that something and multiply it by 3 at the end. You can do the same thing here with the integral, okay? So if I had, going back up here, if I had the integral of e to the 3x plus, 5x to the 4th, I could pull the 5 outside of this integral,
It's like 5
okay?
near the S.
Now, this one right here, the integral of a constant, is actually really easy if you picture it. Okay? I want the area under a curve.
How could you make the integral of a constant?
Oh, just one line.
Straight
Let's
line.
think about it. Yeah, a constant is this, all right? It's a horizontal line. Let's make it a horizontal line, an actual horizontal line. That's much better. All right? So if I'm going from A to B, what do I have?
Rectangle.
I have a rectangle.
So,
How do you find the area of a rectangle? Length times width. Well, since this is the horizontal line y equals c, I know that these sides are c, and how long is this side here? B minus a. So length times width, c times b minus a. Okay? So, don't let the constants mess you up, all right? If you have the constant, just figure out how wide your interval is, what's b minus a, and multiply that by your constant. Okay? So, not too bad. It takes some getting used to. And you're going to have to be careful to keep your rules straight. Keep straight the rules for taking the derivative, from taking the integral, okay? But it's not too bad once you get the hang of it, okay? All right.
Got that.